All right, the part I want to talk about today is is pressure. So when we think about metamorphic rocks, one of the things that they've undergone is a change from one rock to another. And under those conditions, they are exposed to not only higher temperatures, but higher pressures, or different temperatures and different pressures. So remember that depth increasing this way and temperature increasing in that direction. As we go down in depth, temperature increases, and it increases at a rate of 20 to 30 degrees C per kilometer. So we would expect temperature to go up as we go down in depth. Same thing happens with pressure. So if we just change this line to pressure, we see that indeed pressure increases as depth increases as well. Now, the change in pressure normally would be actually that's backwards. So for every 3.3 kilometers we go down, it goes up 1 kilobar in pressure. And a kilobar equals 1,000 bars. But of course, you have to know what a bar is. 1 bar equals 1 atmosphere of pressure, so normal atmospheric pressure, or 14.7 pounds per square inch. So as you're standing around, you have 4.7 or 14.7 pounds per square inch on a normal day on each, or 14.7 pounds of the air pressing down on every square inch that you have. So this sort of pressure that we see here, we refer to that as confining stress. So confining stress confining stress is stress that's equal in all directions. So if we had a box here that was being stressed by confining stress, then the pressure in every direction would be equal. So all 6 sides would experience the exact same pressure. This is the pressure that would be experienced just being buried inside the earth. We experience that as the pressure from the atmosphere. We've got 14.7 pounds per square inch pressing down everywhere. You probably experienced confining pressure or confining stress when you dive into the swimming pool. When you go down, you feel that pressure, that squeezing on all sides of you. So a rock that's experienced confining stress is typically one that is simply buried. So the opposite of confining stress, let me write the definition here. The opposite would be differential stress, and instead of pressure equal on all sides, then we have differential stress, and this time the pressure is so this time it's not equal on all sides. There is a direction of maximum stress. for example, the stress in one direction is greater than the stresses on all the others. That would be differential stress. Now, there are 3 types of differential stress, and we can examine these starting with a ball of silly putty. So probably a lot of you have played with silly putty in the past. And so if I make this into a ball, just to illustrate, then I can take this ball and I can squeeze it. And if I squeeze it, I get shortening in one direction and elongation in the other direction. So with this would illustrate compression. So compression we get elongation that way. Put this back into a little ball, and after get that prepared. Now, what else can I do to it? Instead of squeezing it, how about I pull it? Now the elongation is parallel to the direction of maximum stress, and that is tension. The last one is shear stress. And in this case, the stress is going in parallel but opposite directions, so we get elongation. It's parallel, but as can be illustrated in this deck of cards, if I shear this card set, then the top half is going to go, if I shear it that way, it's going to go that direction, and the bottom half will go in that direction. And that's shear. So this one goes this way, that goes that way. Hopefully you kind of noticed that these look a little bit familiar. This one, convergent plate boundaries. And this last one, we get divergent for tension, and then transform plate boundary for shear. Now we talked a bit about what can happen with differential stress, but I want to give you an illustration of confining stress and how it can change rock. So here is an example of a regular old styrofoam cup and one that's been decorated, same styrofoam cup. Take this styrofoam cup and take it down in a deep into the ocean, say 2 kilometers, and this is what happens. The cup gets shrunk. So it doesn't get crushed. Crushing would be compression, right? So if I don't have a styrofoam cup, I just got this one. But this would be compression, or you could step on it and this would be compression, but it would essentially be flattened. But this one's undergone confining stress. So it's been squeezed in all directions, inside, outside, up, down, and all around. So as a result, the styrofoam was changed in shape, and it just basically shrunk. Instead of smashed or pulled or anything like that, it just shrunk. So minerals will do similar things. That makes the difference between graphite and diamond. Graphite looks very different than diamonds. Diamonds are high pressure, high temperature. Graphite's Low pressure, low temperature, we get difference is in the mineral appearance and their structure, even though they're exact same chemical formula.